We present a robust and efficient method for simulating Lagrangian solid-fluid coupling based on a new operator splitting strategy. To achieve this, we design quadratic incompressibility and viscosity potential energies for fluids based on an updated Lagrangian update rule and SPH discretization techniques. We then propose a unified two-way coupling formulation with barrier-based frictional contact to couple SPH fluids with FEM solids. The separable boundary condition with adjustable friction is enforced with the penetration-free guarantee. Although the resulting scheme achieves strong coupling, it can be very inefficient to solve directly. To tackle this issue, we propose a novel time-splitting scheme augmented by contact proxy, which split the time integration into a fluid phase and a solid coupling phase. Our proposed contact proxy effectively resolves the instability issue caused by time splitting without compromising the consistency of time integration. Additionally, the computational performance is further enhanced by a matrix-free conjugate gradient method and a domain-decomposed solver. In this example where we couple deformable solids with inviscid fluids, the baseline time-splitting scheme produces fine simulation results with 1.7 times speed up. With our proposed time-splitting scheme, more consistent simulation results can be obtained with even better performance. When it comes to viscous fluids, situations get worse for the baseline time-splitting scheme. In this example, we drop a viscous armadillo onto the ground. For baseline time splitting, severe artifacts can be observed at the boundary and the fluid surface cannot finally calm down. In contrast, using the contact proxy, our proposed time-splitting scheme produces consistent simulation results with joint optimization. Similarly, our contact proxy also allows us to robustly separate elasticity from contact potential energy. Our method also supports adjustable boundary friction between solids and fluids. Next we compare our method with several popular SPH fluid solvers and a state-of-the-art solid-fluid coupling method. DFSPH and IISPH focus on incompressible fluids. Though their formulations strictly enforce incompressibility, they don't have a general potential energy form and thus cannot be applied to optimization time-stepping frameworks. While we treat fluids as weakly compressible, our methods can simulate stable fluid dynamics without visually evident volume loss and enjoys the advantage of easy coupling. We then compare our method with elastomonolith, which couples Eulerian fluids with Lagrangian solids. Following their simulation settings, we ran two coupling simulations. Without the need to deal with geometric differences, our method is much faster. Then we evaluate our method in more complex scenarios. We drop 3 elastic elephants with different densities into the water. Our method correctly captures the floating behavior. Our method is able to couple fluids with codimensional materials with penetration-free guarantee. As we slowly twist the cylindrical cloth, the inside water gradually gets squeezed out through the holes. Here we use an elastic spoon to stir viscous cream in a bowl. The spoon gets deformed due to the contact with the cream. Here we demonstrate our framework can simulate the coupling of materials in arbitrary codimensions, including fluid particles, rods, thin shells, deformable solids, and rigid bodies. We launch an angry elastic cow with a slingshot. The cow hits through the wall and then falls into the water. Finally, we show a scene where a mannequin dressed in a multilayer skirt kicks in a large water pool, involving complex interactions between fluid particles and garments. Our method well resolves the contacts among fluids particles, thin garments and rapidly moving complex boundaries with penetration-free guarantee.